Okay, thanks very much for the invitation. I'll tell some story about something that I found interesting recently, and also I don't fully understand. Yeah, I guess all you guys' eyes get tired, so it's good to use blackboards to get relaxed. Something like that. I mean, we want to understand some kind of integrable hierarchies, like stories come from starting from KDV and NKDV, for example, and you go to ADE type integrable hierarchy, and all the way down to arbitrary Calabi-Yau geometry. I want to describe a single construction which unifies all of this stuff. By actually a single construction, in terms of like a topological stream field theory. And actually, I'm going to work with speed model in my talk. And in this case, it's a stream field theory described by so-called Kodaira-Spencer gravity, and that's my title. So here's the motivating example to start. Yeah, this talk cannot be harder than this example. So you try to look at entire series expansion for this function, u over t, and you find like 1 plus u over t plus u squared over 2 factorial t squared, and so on. And then you try to observe something interesting. You promote this variable u to be a function for one variable, and introduce. Yeah, this is going to be some old story. Introduce a Poisson bracket. For example, the Poisson bracket in this case is given by these two functions are given by the derivation of the delta function. Then you look at this Taylor series expansion. You just collect all of the powers to build up some Hamiltonian functions. And you check this Hamiltonian functions commutes under this Poisson bracket. And this is actually a familiar example. This is an example of dispersionless KDV. This generates the dispersionless KDV integrable hierarchy. And in general, what's going to be happening is the following. In general, for arbitrary Calabi-Yau, X Calabi-Yau, you're going to replace this variable u by some, I'll explain, but some kind of Kodaira-Spencer gravity fields here. And this exponential map is replaced by Saito's primitive form. And so let me explain a little bit what's happening here. Which one? You gotta contain positive non-negative powers in T, and some other stuff like a polyvector field and so on. I will explain. Okay, so first let me explain a little bit about this Kodaira-Spencer gravity, which is proposed by Bartschek, Sokoli, Ogrivafa. Let's call this one BCV theory. And then I'm going to describe a version that I generalized with Kevin Costello. As follows. So we try to understand, say, X Calabi-Yau. Gonna stop it. Okay. Oh. Okay, it's fine. So X is a Calabi-Yau. And then we work with polyvector fields on this Calabi-Yau, which is given by like the book complex valued in these holomorphic polyvectors. And in this theory, the field content is described by the following complex. It's these polyvector fields valued in formal power series in one variable, t, and t plays the role of the gravitational descendants. And this is a complex with an interesting differential. Let's call this one Q. It's a del bar plus the del operator. And this is the bar operator. This del operator is the divergence operator. With respect to the Calabi-Yau volume form that we choose. And you can also try to write down action functionals for the theory. I will just sketch what's happening. Like this one satisfies some kind of a mass equation for this kind of classical interaction. And in this so-called BRC-BV formalism, I will not write down formula for this one, but just let me explain that this is basically, this equation is equivalent to somehow the structure of differential graded Lie algebra for this space. And this is a differential and the Sheldon bracket. I just want to make one remark that this implies that the equation of motion of the theory is basically the same thing as the Morikawa equation. But there's an interesting feature here that if you try to write down equation of motion, just Morikawa equation from this DGOA, there's no, somehow you cannot write down action functionals. And I have to perform some nonlinear transformations to make this equation of motion into some form that we can write down action functional. That's an interesting feature of the theory. Okay, so here's the main construction. Let's consider B model. On the product space. It's very strange that the integrable hierarchy will live on an extra curve. So we make an extra dimension, which is also Calabi-Yau. So we can formulate B model on this product space. So iterate the dimension of the Calabi-Yau. And for the B model, we work with BCV theory on the product space. And actually, we get something interesting. Like we can twist our differential a little bit. So I change my, now you see like you have two Calabi-Yaus. I change my differential, let's call this one Q epsilon, which is a complex here, by the d-bar complex plus the other side is the same, but I have two divergence operators from X and from C. The first one, let's call this dx, and introduce a parameter, let's call epsilon. DLC. Let's call this one Q epsilon. Now, starting from here, you can get an effective theory in 2 dimensions. It's a 2D Caillard theory. Let's call this theory EX. And there's 2 parameters here. Here, one is the quantum parameters from the gauge theory. Let's call this one H bar. There's another parameter here. Let's call this one epsilon. And then by from the construction, this guy, the BCV theory, satisfy a so-called quantum mass equation, BV quantum mass equation, which actually is a general feature for closed string field theory, as shown by Ziwabak, for this kind of BCV theory on a product space. And by general nonsense of this kind of doing Buick quantization, this one leads to saying that the theory here satisfies some kind of quantum mass equation. So I will explain to you that just from this abstract nonsense, you end up with infinite many commuting operators, which generate this kind of gateway example. So you have to learn this. Yeah, the goal is to show like this. This mass equation just implies the integrable hierarchy. Oh, thanks. Probably have to. Yeah, it's tricky. Thanks. I can do it. Yeah. Thanks. Yes? For? This better? Better? Okay, that's the upshot. Now let's see what's happening. First, there's a technical theorem somehow which says the following. So the quantum mass equations for this kind of chiral 2D theory in a very general sense, this kind of equation has a pretty geometric meaning. It's given by somehow can be viewed as saying that it gives rise to some kind of integrable evolution of the corresponding vertex algebra parameterized by some background fields. Of some background symmetry. This is the technical lemma in the preprint I listed in the beginning. So let's assume this and try to see what's happening. Now, let's try to look at the theory we have downstairs. So for this guy, the field content because it's an effective theory on zero modes, and you see that the field content for this theory is given by harmonic stuff on the Calabi-Yau, harmonic polyvector fields. Yes, can you see from here, or this harmonic polyvector fields? No, this is the zero modes along the x. We don't do anything on the copy of C, so actually we get a polyvector field on C with a gravitational descendant. And that's the field content of the theory downstairs. And actually, this story also works for London-Ginsburg, that if you work with a non-compact Calabi-Yau with a London-Ginsburg superpotential, and this guy will be replaced by the Jacobian algebra. But anyway, that's the field content downstairs. Now, Inside this one, you can see that not everything is propagating, and there are huge background symmetry. So you can specialize to some of them. So for example, you find a abelian subgroup, a abelian subalgebra of this background symmetry generated by this harmonic polyvector fields. Now, for this part, you choose a abelian subalgebra, which is generated by like powers in T, and one polyvector along this C direction. This is like translation along this extra dimension. And you can see easily that this is an abelian subalgebra. The bracket is 0. And by this general nonsense, if you look at how this background symmetry is coupled to some kind of operators on the what is the algebra, you find basically as a consequence of the theorem, you can commuting chi operators. For example, of the form like, let's say, take any kind of elements here, it corresponds to a current. Now, it depends on two parameters. One is h bar, the other one is epsilon, I wrote down upstairs, and some kind of form. So if you get an infinite many of them like, coming from this data, and because this is abelian subalgebra, and this implies that this chi operators by construction commute. Now there's something interesting that you can look at the behavior of these parameters. Now you take a limit when you set, for example, h bar goes to 0 and epsilon goes to 0. This is like classical, somehow like behave like classical dispersionist limit. Actually, you get the integrable classical integrable hierarchy studied by Dubrovin. That is formulated on any kind of actually Frobenius manifold. Now you can do something more fun, like if you just set epsilon goes to 0, you find actually a deformation of this classical system. In the case of a semi-simple situation, it's very convincing that it should lead to a construction by Dubrovin-Zhang. They find somehow a canonical deformation of this this integral hierarchy on this Frobenius manifold in the case of in the semi-simple situation. But you can try to understand what's happening for these two parameters, and also I don't know whether this story is somehow related to Microsoft Saakashvili story, and yeah, it's something like worth exploring. So I probably stop here. Thank you very much for attention.